down. Today's speaker, Mercedes Lopez Morales, grew up on Tenerife, which is one of the Canary Islands,
Right.
which is a part of Spain.
Yes.
And she did her undergraduate studies at the University of La Laguna, famous university, and the Canaries anyway.
The Canary Islands.
From there, she came to the U.S. for her graduate studies at the University of North Carolina in Chapel Hill. And she first visited CFA for a week in 2003, a year before finishing her PhD.
Right.
I remember that week well.
Me too.
And she came to learn how to use TODCore, and Willie Torres showed her how to use TODCore, and she went off and applied that precious new knowledge to an analysis of GU booties and put out a paper that received quite a bit of attention for a paper on a double-line eclipsing binary. And that signaled her interest in deriving fundamental stellar parameters from observations, which she did for a number of years. And after 6 postdoc years in Washington, D.C. at the Department of Terrestrial Magnetism, first as a NASA astrobiology researcher and then as a Hubble Fellow, she returned to Spain for a couple of years.
That's right.
And 10 years ago, we managed to convince her to come to SAO and join the HARPS North collaboration, because we had access to 80 nights per year on the Italian 3.6 meter Telescopio Galileo Nazionale. And while some of us endured the long trip to the Canaries to observe on HARPS North at Roque de los Muchachos Observatory, Mercedes didn't seem to mind a layover in Tenerife. And with great foresight, Mercedes evolved an interest in the study of exoplanet atmospheres. For example, proposing the detection of molecular oxygen with future facilities such as the Giant Magellan Telescope. And she had a very large program on HST for transmission spectroscopy. And that has positioned her well for the revolution in the spectroscopy of exoplanet atmospheres enabled by JWST, which is the topic of today's colloquium.
All right. Well, thank you, Dave, for the introduction, and also thank you in particular to the colloquium for inviting me to give this presentation, which I was just telling Jonathan McDowell, who gives the talk next week, that it's really weird to be giving the colloquium in your home institution. But so as Dave was saying, and most of you know, I work on exoplanets, all the way from Jupiter's to like Earth-sized planets with a particular soft spot for detecting and characterizing their atmospheres. But before I start showing you any of that, I wanted to introduce to you the Exoplanet Atmospheres group at SAO, or CFA, because I realized that with about 2+ years of pandemic and a lot of people coming and going, we probably don't know everybody's faces anymore, and this is a good way to showcase the people who are here working on this kind of stuff and also working on radio velocity, mass measurements, and if you see them around, you can say hello and ask them what you are doing. And I'm so proud of working with these people that most of the work that you're going to see here, is always thanks to everybody, not just me. And we have a postdoc position opening, so I figured that I could advertise that as well. So going back to the actual talk, I see a few people in the audience who are actually exoplanet experts. Please bear with me for the first 10 to 15 minutes because I need to bring everybody up to speed, especially the younger people who don't work in the field. But I promise to you that if you stay awake after the first 15 minutes, you're going to see really cool stuff. So please bear with me. So, as most of you know, as all of us know, we only knew of a few planets for centuries. And even during the 20th century, up to 1995, we still only knew of the planets in the solar system, and that was it. But about 3 decades ago, things started to change, because we discovered the first exoplanet around another star. And after that, with a number of techniques that are shown here in different colors, we have discovered to date about 23,000 candidates. And of those, over 5,000 are confirmed exoplanets. So this has been crazy. However, if you see the distribution of planets that we have here, you see that we have a lot of things. We have Jupiter, Saturn, some Neptunes. We don't have any Uranus yet. And we have some rocky planets, but they're still not quite like Venus and Earth, or Mercury or Mars. Those are the rocky planets around M dwarfs, which I will show you something about that at the very end of the talk. But, the pace at which we are discovering planets is not slowing down anytime soon. With existing missions such as TESS and Gaia, and upcoming missions such as the Nancy Roman Space Telescope, and also a bunch of instrumentation from the ground. The new ELTs coming, and very sophisticated instrumentation in those new ELTs. The expectation is that if the pace of discovery continues, by 2030, we will have about 85,000 candidate exoplanets. And even if only 15 to 20% of those get confirmed, we will have about 15,000 confirmed planets to look at. And now, if you look at here, now we will have, by the end of this decade, hopefully, we will have things like Venus and Mars, but we still will not be sensitive to things like Mercury and Mars. So the chase will continue, right? So, a portion of the exoplanet community, that's what they do. They try to find more planets, going all the way down to the bottom to the smallest possible mass or radius. But in the meantime, a fraction of us have gotten interested in the atmospheres of the planets. We actually want to know what the physical and chemical parameters of these planets are. And with that information, we want to be able to answer some questions that have been lingering about for decades, if not more. One of those questions is how planets form and evolve. That's one of those questions. Another question is what are these planets made of? And what the different planets look like when you actually look at their spectrum. And another question is how diverse are exoplanets, right? Especially what physical and chemical property, parameter space they cover, and especially in particular, how do the solar system planets actually compare to these extrasolar beasts, right? So I dare to say, and I already said this when I gave the ITC launch a few months ago, I dare to say that exoplanets is now at the stage that stellar astrophysics was pretty much 100 years ago. When Cecilia Payne finally figured out, what all these crazy lines in the spectrum of stars look like, and she started to tag those lines to chemical elements, that's where we are with exoplanets. And by finding the chemical composition of atmospheres of exoplanets, which is what we are trying to do, using similar techniques to what they were using 100 years ago, we can answer the previous questions that I was asking about. So this is how we do it. Again, for those of you in the audience who work on exoplanets, please bear with me. But for those of you who don't, this little explanation is going to give you what you need to understand the spectra that I'm going to show you later, okay? So we basically have two main techniques to study exoplanet atmospheres. One of them is direct imaging. That one is easy to imagine. You block the light coming from the star with a coronagraph or something. You find a little planet, you put a slit on it, and you get a spectrum, and voila, there is a spectrum of the planet, and you can look at it. However, this technique is a little bit behind because our technology is not quite there yet. We can do Jupiters, young Jupiters, but basically nothing else. So what we are doing now is using this other technique, which uses transiting exoplanets to do that science, to look at the atmospheres of the planets. And what this technique does, as some of you know, is we take advantage of the geometry of the system, and we look at the ones that happen to pass in front and behind the star every so often. When the planet goes in front of the star, we look at the light that percolates through the atmosphere of the planet. When the planet goes behind the star, we look at the light that is lost from the system. And we also have this other technique, which I'm not going to show you yet because those results are not out yet, but we have these other techniques where we follow the planet along, along the orbit, and we can do like these phase maps where we see light coming from the planet at different angles. So this is basically how we're doing it. And this, again, if you don't work on this, I understand that this is a little bit, conceptually it's a little bit convoluted, but just so you know, so you understand what you're going to be looking at later. So basically, the way we do it is we point the telescope at the star when the planet is transiting, and we monitor it. We take spectra continuously before the planet goes in front of it, while the planet is in front of it, and after the planet is in front of it. And what we do is then we take that spectra, we bin it in different colors, and we plot the light curves of the different colors of light. And this is like a stellar astrophysics again, right? So everybody took in, their stellar astrophysics class, like everybody learned about the idea of opacity. This is exactly the same. Different chemicals give you a different opacity, right, in the atmosphere of the planet. So basically what happens here is that when you hit a wavelength, when you hit a color where some element is absorbing, the opacity of the atmosphere of the planet changes, so the planet looks bigger. So what we do is we look at the different colors of the light, and we look versus how deep the transit is at the different colors, and that gives you an idea of what elements are in there, because the size of the planet changes if it is observed, if that element is there and the light is being absorbed for that element. So this is our spectra. Notice that this is where people get super confused. Notice that our spectra are upside down, right? So those bumps that you see going up, that's absorption in a stellar spectrum. So anytime that you see a bump going up, that is absorption by an element. And this is, as you can see, the technique is not super complicated. It's fairly basic. The problem is the precision that you need. So these changes in the size of the planet that we are talking about, if you have a Jupiter-sized planet around an M dwarf, for example, those changes in the size of the planet are of the order of 10 to the minus 3. If you have a Jupiter-sized planet around a G dwarf, that's of the order of 10 to the minus 4. If you have a terrestrial planet around an M dwarf, those changes are of the order of 10 to the minus 5. And around a G dwarf, those changes are of the order of 10 to the minus 6. So this is almost like nanotechnology going on here. It's not quite there yet. But as you can see, that's why this is complicated, because we need to push the instrumentation to the limit of what they can do. And this is basically what we have been doing for the past 20 years. We have been using instrumentation available, mostly the Hubble Space Telescope, Spitzer, and the Magellan telescopes in Chile, among other ground-based telescopes, to actually try to find these little changes in the depth of the transit as a function of color. And this figure that I show you here, that kind of tries to represent, the classic spectral type diagram from stars. This is the first attempt to do something like that with exoplanets. This figure more or less summarizes what we have been able to do up to last year. So far, we have been able to observe with existing instrumentation about 60 extrasolar planets, the atmosphere of about 60. Here you only have 10, but it kind of shows you the idea of everything that we have been able to do has been from about 0.3 microns to 1.7 microns. So that's optical and very near infrared. We have been able to do spectroscopy with that, mostly with Hubble, but also from the ground. And then Spitzer has provided 2 points, one at 3.6 microns and another one at 5 microns, that we have tried to use, to anchor the spectrum of these planets. So basically, we had hit the limit. Last year, this is basically how well we could do. And we have learned a number of things, but I would say not enough. One thing that we have learned is that only about 7% of the planets have clear atmospheres. Everything else, clouds were getting in our way, and we weren't able to see much. There is some features that we have been able to detect. For example, you see that, like this feature here at 1.4 microns, that's water. So you see that we have been able to detect water in pretty much every planet that didn't have a lot of clouds and let us see through a little bit. So water seems to be plenty out there, These are all Jupiters, by the way. So we have been able to detect potassium and sodium. But there is something going on. There's some of the planets show potassium, some of them show sodium. They don't seem to both show at the same time. So something is going on there that we couldn't really understand. And another thing that you see from this diagram is this is meant to be from the top to the bottom. It's meant to be cloudy, like a cloudiness index. Like the planet at the very top, it was very clear. The planet at the very bottom is very cloudy. We don't have a clue of what causes these physical properties in the planets. We have looked at everything, all kind of parameters like, exoplanet temperature, distance from the star, irradiation, all kind of stuff, and we haven't been able to find a correlation. So we were pretty much lost. And another thing that we have been limited up to last year is that we couldn't. We could see water and some, elemental abundances, well, some elements like sodium and potassium, but we didn't have enough spectral coverage to see anything else. In particular, things like carbon molecules. And that's super important because, as I will show you later, carbon is one of the critical things to be able to understand how these planets form. So that's where we were last year. Everything changed when the JWST launched successfully on December 21st, like Christmas Day 2021. And everything that I'm going to show you from now on is JWST results. Literally 48 hours of JWST observations. So you get an idea of how things have changed, right? Just from the fact of having put this telescope up into space and having it work very nicely. This is what Hubble could do. And remember that this is a logarithmic scale down here. So this is what Hubble could do. It could do ultraviolet to the near infrared. This is what JWST can do now. It can bring us all the way out to 30 microns. And it has 4 different instruments that you see here. And they cover, like all modes of spectroscopy, direct imaging, and so on. So this on itself, combined with the fact that the aperture of JWST is about 7 times larger than the aperture of HST, is part of the reason why all these groundbreaking results are happening. Now, another thing that you might not realize, and this is why at the beginning of my talk I say, the telescope that changed exoplanets in 100 years, in 100 days, is that to this day, right now, there is about 10, well, and this happened even before the telescope launched. About 10,000 hours have been already scheduled for programs across the board with JWST. And this was part of early release science programs, guaranteed time observations for people who have been working on the telescope, and then the first open call for proposals, that was cycle 1. So we had already 10,000 hours scheduled, of which 25% of the time was dedicated to programs that are going to be observed exoplanets. And there is about, this diagram here shows the size versus the equilibrium temperature of all the planets that already have scheduled observations on JWST. So there is about 60 points there. That's as many as we had managed to actually observe an atmosphere of over the past 20 years. And all these observations have to happen by the end of this year. Maybe some of them will spill over into 2024 a little bit, but this is the stuff that we're going to have in hand by the end of this year, just to give you an idea of what's happening. Right now, and just because of the duration of the talk as well, and also because of what has come out, I'm going to focus the rest of the presentation in these 2 planets that I highlight here with the green circles. One of them is, the one at the top is a Jupiter with a temperature of about 1,000 Kelvin. That's WASP 39. That's part of the early release science program. And this other one here is the first observation of the atmosphere of a terrestrial planet. Like, this planet has exactly 1 Earth radius and a temperature of about 600 Kelvin, which is just a little bit cooler than Venus. So this is what I'm going to show you in the remaining of the talk. So first, let's go with the Jupiter-sized planet, WASP 39. So as you see here, WASP 39 is a Jupiter-sized planet, slightly larger than Jupiter, but it actually has the mass of Saturn. So, and it's about 7 times hotter than Jupiter. It has a temperature of about 1,000 Kelvin. So this thing is fairly puffy. And these observations that you see here, this is probably the best observations that we had from the ground. Before JWST, both from the ground and with HST. And you see here that on this planet in particular, we could already see clearly some things like water bands. We could see sodium, and we could see a tiny hint of potassium. And that's all we had. And with this data, we could already tell you some things. For example, we could tell you what the metallicity of the planet was, right? And that metallicity, when you plot it in a mass metallicity diagram, and you compare it to, for example, the planets in our own solar system, you see that this particular object appeared to have a metallicity that was like a factor of 10 to 20 times higher than the metallicity of Saturn and Jupiter. So at the time, this was published 3 years ago, the last one. At the time, we were saying that there was something really odd about exoplanets. You know, we were saying that some different formation mechanisms must be happening around this with these Jupiters because their metallicity doesn't look like the metallicity of the gas giants in the solar system. So that's where we were. But we couldn't tell anything else because, as you see, we couldn't do any other molecules. So this was precisely why this target was selected for the early release science program. For those of you not familiar with JWST, at the very beginning, this was about 5 years ago, a Space Telescope at NASA. This was at the time when JWST was meant to last 5 years, 10 years if we were lucky. So everybody was scrambling and saying, we really need to give data like really, really early so people can figure out how to use the telescope because if it is as slow as everything else so far, we are going to run out of telescope before people figure out how to use the data. So they gave, I think it was like 500 hours to, I think it was 13 different early release science programs on a wide range of topics, from planetary science to cosmology. And we were awarded this particular program on transiting planets for which they gave us 78 hours of telescope time. And basically what we argued in this program was that we needed to be able to use all the possible modes, or as many modes as possible on the telescope, to figure out which ones work for exoplanets and which ones didn't, because otherwise we would be wasting our time when applying for telescope time. We wanted to test how long could the telescope actually follow a target and the data to be precise enough. So that was the second program that you see here for a phase curve. And we also wanted to test how precise could we get? Because the numbers on paper said that the telescope, the objective goal or something like that was 30 parts per million precision. If that was true, terrestrial planets were hopeless. So we better start to build something else already. So these programs, in addition to doing a little bit of science with exoplanets, were actually meant to test that. And they were meant to also produce pipelines and information for the community so they could quickly jump into exoplanet data and start producing science with it. So between July, so what I'm going to show you here is the first project, the one in which we had to test the different instruments. The other data sets, we have them in hand, but they're not ready to publish yet. And so basically, for WASP-39, between July 10th and July 30, we got 4 different transits on each one of these instrument modes that you see here. Near spec prism, going from 0.5 to 5.3 microns. Near cam, with this filter that gives you data between 2.4 and 4 microns. Near SOS, that gives you data between about 0.6 and 2.8 microns. And near spec with this 395H GRISM, which gives you data between 2.8 and 5.3 microns, but this one is a higher resolution. It's about a resolution of about 3,000. These are the data. I realized that you cannot read the labels, but I had to find a way to actually show you the whole thing in one place. These are the data from the 4 different instruments. You see a lot of wiggles in there. So there is signal in there. And just to give you a little bit of insight of what those wiggles are, and actually this is what I'm going to be focusing on, you see that we have found potassium, water, pretty much all the water bands that are available. We have found sodium, we have found carbon dioxide, and we have found sulfur dioxide. So I'm going to go now into, there is already 6 accepted Nature papers on these observations. And what I'm going to show you here is basically based on information that has been published in these papers. So let's go with the first detection. This is a portion of the PRISM data that goes between about 2.8 microns and 5.3 microns. And what you see here, the discovery here that you probably saw it announced a couple months ago, is that, well, first of all, we detect water. We detect water clearly on this band and many other bands with significant levels larger than 20%. Previously with HST, if we hit 5%, we were jumping, like we were so happy. So now we're just hitting 20% easily with water. Carbon dioxide, we actually get like 30 sigma detections of carbon dioxide. And this was like, you just had to look at the data and it was there. So why are these two detections of water and carbon dioxide so important? Well, so let me see. Remember that I was telling you about planet formation, right? So there's a theory by Karen Obert that basically tells you that if the planets form, like gas giant planets form beyond the waterline or beyond the ice lines, they should be enriched in these heavy elements, right? And in particular, their carbon to oxygen ratio should be different than the carbon to oxygen ratio from the host star. And what we find in this case is that the carbon to oxygen ratio, based on that water and CO2 detection, is between 0.3 and 0.46. The carbon to oxygen ratio of the host star is 0.58. So in this case, the carbon to oxygen ratio is lower. That means that the atmosphere of the planet has a lot more oxygen than the atmosphere of the star itself, and also more oxygen than carbon. That's already telling us something. Another thing that we can discard from the data very, very clearly is that the carbon to oxygen ratio is not larger than 1. And that also has implications from where this planet formed. Basically means that it couldn't form farther out in the disk where carbon is abundant. So in this case, you would have more carbon than oxygen. So basically, just with these observations, for the first time, I would say, we can definitely say that these planets must have formed between the water line and the CO2 line. So we basically can place like a very strong limit to where the planet formed. And somehow this planet has migrated in. And that's another thing that we know now that is true. So that comes from this second detection. Never seen before like this. We detect potassium. We detect potassium super clearly. Potassium has been a sneaky one because if you try to observe it from the ground, it overlaps with the molecular oxygen band from our own atmosphere, so you can't pull it out, really. And with Hubble observations, the resolution is not large enough. So potassium, sometimes you see it, sometimes you don't. So you don't know if it is that the planet doesn't have it or that the resolution of your data doesn't allow for it. But here, there is a very clear detection of potassium. And this is with the NIRISS data, which has a resolution of about 700. So here, you see very clear detection of potassium. 6.8 sigma. And not only that, but just the fact that the NIRISS data also covers some water bands allows us to detect the potassium to oxygen ratio in this particular planet. And what we find is that that ratio is supersolar. That means that the planet has more potassium than the star. And what does that mean? I mean, and this is like as timely as it gets, right? So somebody, a few months ago, published a paper that basically said that if gas giant planets migrate, these planets should be, first of all, they should be rich in water because they come from further out, but they also should be rich in refractory elements, which are sodium and potassium, because they will be accreting those as they migrate in, because those elements are stuck in like tiny little rocks or whatever in the way in. So if the planet is migrating, it should be rich in potassium, and the CO ratio should be larger than the star. And that's exactly what we find. If you see these models here, basically the potassium to oxygen ratio is between 0.2 and 0.4, which is 1 to 3 times solar. And that prediction, I just went a little bit too fast, but that prediction basically, let me go back for a second, that prediction totally puts the picture of like how this thing formed together. Because on one hand, we see that the CO ratio is less than the star. That means that the planet must have formed somewhere between the water ice line and the CO2 ice line. And then the potassium to oxygen ratio is actually larger than the star. So that means that that planet came in Slowly but surely, it came in. So now we know that this planet actually formed somewhere else. And another thing that we knew, that I forgot to mention before, is that the metallicity of the planet is about 10 times solar. It's not the 150 metallicity that we were seeing with the JWST data at all. It turns out that it is 10 times solar, and I will show you that to you in a little bit and explain why that is important as well. The third result, and again, this is from the same data set, the third result that I wanted to highlight is this mystery molecule that we found. And this was a little bit of a headache, but at the same time, I mean, it was super fun to do. So, I go back to the same spectrum where I show you the water and the CO2 initially, and you can see here there's a little bump in that region. Then local thermodynamical equilibrium models cannot fit that bump. So the theorists, the modelers in the early release science team, group, were scratching their heads, saying, what's going on, what's going on, what's going on? We have no idea what's going on. And actually, I need to give a shout out to the Hydron team here at SAO, and especially, their high temp line list, because that line list, combined with people that have photochemical models, actually figure out, what is that bump in there? And it is sulfur dioxide. This one truly took us by surprise, and I will explain why next. But first, I will show you here the results of this modeling for sulfur dioxide. So these are actually now non-equilibrium photochemical models. And as you see here, we use different solar metallicity models. And you see that here very clearly, a 10 solar metallicity model fits the data really well. And what is important, not only the fact that we discover sulfur dioxide, what is important is that we also discover that is a very sensitive indicator of exoplanet atmosphere metallicity. Because as you see here, before we had been using water, we had been using CO2, and as you see here, the 3 different models basically give you fits that are more or less equally good. When you look at the SO2, clearly the 10 times solar metallicity model is the one that fits the data. So we have found a much better metallicity indicator. But again, why SO2 is actually so exciting for us? It's because of photochemistry. I mean, this thing that you're seeing here, the little bump, is the first detection of photochemistry in an exoplanet. And photochemistry, is important because, it tells you about atmospheric composition and so on. On planets like Earth, it actually tells you about habitability, right? For example, photochemistry is responsible for the formation of the ozone layer on Earth. And that's where we're here, because oxygen gets up there, ultraviolet photons dissociate the oxygen, individual oxygens go and group back, in teams of 3 as ozone, and that's what protects us from the ultraviolet radiation from the sun. So photochemistry, in the case of a gas giant, is a different process. In the case of a terrestrial planet, SO2 is pretty much ubiquitous, because you see it on Earth, you see it on Venus, you see it on Io, and that has to do with volcanism. But when you actually go to a gas giant, the process is totally different. What we think is happening here is that, in normal conditions, if the planet wasn't irradiated, any sulfur on the planet would be on hydrogen sulfide. But the ultraviolet radiation coming from the star actually is dissociating the water, and it's creating OH and H that actually react with the hydrogen sulfide, and somehow any sulfur that gets left out combines to form sulfur dioxide. So this is the overall reaction that you see here. And this is great because it basically means that we have discovered photochemistry in exoplanets. It seems to be everywhere. And that is promising for a field where we weren't even looking for this kind of stuff. So now, I've shown you things that we have found. Now I'm going to show you something that we didn't find, which hopefully you also find interesting. There is no methane. We can't find methane anywhere. And that's actually, it's a bad thing and it's a good thing, right? It's a bad thing because it's exciting to find methane, right? But it's a good thing because it's actually telling us a lot about what's going on with these planets. So this is a little bit busy. These plots are a little bit busy, but I'm going to try to explain to you what we are seeing here. So the points are the data, And then the different lines with the different intensities of pink are telling you, in this case, we fix the carbon to oxygen ratio of the star, of the planet, and we change the metallicity of the planet. And in this case, we do the opposite, right? We fix the metallicity to 10 times solar, which is what we are finding from other things, and then we change the carbon to oxygen ratio. And you're probably wondering, Mercedes, those models don't fit, and that's the point, right? So it's like, so there is no methane. And actually, the combined information between you don't have methane, but you actually have a very strong CO2 band is definitely telling you that the atmosphere is metal rich. Because if you didn't have things like oxygen, but you still had carbon, all the carbon would combine with hydrogen, but in this case, you have a lot of oxygen around, so you get a lot of CO2 instead of methane. So that's one key piece of information. And another key piece of information is that, in this case, none of the models actually fit. And so what we conclude from this particular fitting here is that our inability of simultaneously fit the methane and the CO2 in this particular case is because we weren't including clouds in the model. So this planet, which initially from the Hubble data we were saying, you know what, this planet doesn't have any clouds, we see all these features, it actually does have clouds. And once you include the clouds, it's hard to see, it's that gray model, then everything fits. So methane, even though we don't say it, is actually telling a lot of the story here. And it actually explains, there's this big question from Hubble data for cooler planets. It actually explains why we're not seeing methane in cooler planets with Hubble data, because there should be a signal at 1.4 microns and we're not seeing it. Maybe the answer is that all these things don't form in situ, they form further out, and they're all metal rich, like the planets in the solar system. So we might have, this is only with one data point, but we might have found why we cannot find methane. So just to summarize quickly this part of the talk, this is what we have learned so far with just 39 hours of data with JWST. We are detecting new species that we had never seen before, like CO2 and sulfur dioxide. For the first time, we're providing very strong constraints on carbon to oxygen and, for example, potassium to oxygen ratios, which are actually consistent with migration and formation scenarios. So we now can tell you where this planet formed and how it migrated. For the first time, we have found a way to measure the metallicity of these planets to high confidence in that. So now we know that if the CO2 and the water don't do it, we need to look for sulfur dioxide, and that will provide very high constraints on the metallicity. In this particular case, the information from the metallicity is crucial because you can place constraint on, for example, like core accretion models. So what this means, what the metallicity of this planet means is actually that this thing formed by core accretion, no gravitational collapse of the disk. Because if it was gravitational collapse, the composition of the planet and the atmosphere would be similar, but they are not. So core accretion is the one that allows for the heavier things to collapse first, and then the planet to accrete a gas envelope. And this is what is happening in this case. And also, it tells you that the composition of Jupiter and Saturn are consistent with this kind of planets, so maybe they all form the same way. And also the first evidence of photochemistry in an exoplanet, which is promising for the detection of life in the future in other planets. So quickly, I wanted to give you, before I move to the terrestrial planets, I wanted to give you 2 hints in here. This is actually the data from the 4 instruments combined. So, it looks beautiful. And one takeaway from this that I want to give to you is that the instruments are working so well. I mean, the data are superb. And all the instruments are actually giving results that are fully consistent one with another. So basically, like every single instrument that we have tested on JWST can do exoplanet science easily. The second thing is that all the results that I've shown you before, like up to now, they don't even involve a lot of modeling. These are all software forward models, but the modelers in the ERS team are now like working pretty hard on doing all the modeling, like proper retrieval models, to show like a full picture of what the planet is made of, even give you different abundances of different molecules and so on. But I'm not going to go into that. You should go to Ryan McDonald's ITC colloquium on Thursday, because he's going to show you all this stuff. So if you're interested, go to Ryan's colloquium on Thursday at 11. So okay, quickly now, because I know that some of you have been waiting for this one. So let's move now, this is the last part of the talk. Let's move to the actual terrestrial planet that we have down here. This planet is called LHS 475b, which probably means nothing to most people. It is exactly one Earth radius planet, and it orbits an M dwarf, which is about 30% the mass of the Sun, and it is at a distance of 12 parsecs. This project is not part of the ERS observations. This is actually a separate project, and basically you see here like all the members of the team for that particular project. And this is submitted to Nature, but Nature basically has waived all rights, and we can show this stuff everywhere. And it was actually presented at the AAS, and there was a press release about this 2 weeks ago. So why is this science so important? Well, for those of you following this kind of science, you know that we are trying to find Earth-like planets. And with the current technology that we have right now, we can't get yet to an Earth-like planet around, like a Sun-like star. So for years, people have been talking about this alternative of like looking for Earth-sized planets around M dwarfs, because those are closer, they're smaller. So technically, it is feasible to observe those planets. But now, the big elephant in the room has always been like, okay, well, M dwarfs are like pretty active, like they give off these huge UV and X-ray flares. So, like the atmosphere, like the environment that these planets are into is pretty harsh. And more likely than not, these planets cannot retain atmospheres. And a planet with no atmosphere is more than likely not habitable. So one of the big questions right now is, just because of the environment conditions, do terrestrial planets around M dwarfs can actually retain atmospheres? And this is how this program came to be, right? So we basically have that program on JWST has 5 planets. This is the first one that we observed, and Dave is going to love this one. So this is actually a TOI, like LHS 475b now. When we got the data, or when we got the proposal approved, wasn't even a planet yet. It was a target of interest from TESS. It was TOI 910. And as you see in the TESS light curve, it has like what appears to be very, very clear transits, but it had not been confirmed as a planet. And the reason why it had not been confirmed as a planet is this one. So the host star, which we now know is the host star, is this red star here, it's an M dwarf. And there is another star that projected in the field is at a separation of 18 arc seconds. In principle, everything is good, except that the TESS pixel resolution is 21 arc seconds. So in the TESS data, those 2 stars appear in the same pixel. So their light is basically blended. So even though TESS was seeing like a really nice transit, we couldn't tell which one of the 2 stars the transit was coming from. But somehow, we managed to convince the time assignation committee that that was okay. Because if this planet has a radius of 1 Earth radius, it had to have a mass of about 1 Earth masses. Because based on just observations that we have from the solar system, anything that has a radius of 1 Earth radii or less is rocky, and it doesn't have a big, large gas envelope. So this planet had to be rocky. And somehow, the TAC bought into it, and it actually gave us 3 observations for this particular target. So the first observation was in August 31st. Shortly after, September 4th, we had another observation. We actually had a 3rd attempt on September 27th, which didn't go well. And that one is rescheduled for next summer, for this summer. So hopefully, we will have a 3rd observation soon. So, and these are the results from the 2 transits that were successful. Again, this was done with near spec 395, so we have data between 2.8 and 5.3 microns. This is an Earth-sized planet. I mean, that looks like the transit light curve of a Jupiter to me, but it's not. It's Earth-sized. And you see that there is a little bit of a slope. That's actually a systematic with the data. And the precision of those data points is, on average, we reach a precision of 15 parts per million. So, but this is the white light curve, basically. This is like you get all the spectra, and you integrate all the light, and that's the precision that we can achieve. So now, if you do the same trick that I was telling you at the beginning, you get the spectrum, You bin it into different bands. In this case, it's about 60 bands. And you look at the changes in transit depth. The black points here, that's the spectrum of this planet. It's flat. But that flatness is telling us a lot, because the yellow lines that you see there, those are 3 atmospheres, which actually contain hydrogen. They're hydrogen-dominated atmospheres, and different amounts of solar abundances, of solar metallicities, right? So we can discard confidently that this planet does not have a hydrogen atmosphere. And that has been a very good, a question that has been going, around for like a few years now. They say, well, every planet should form with a hydrogen atmosphere. Even if it is a terrestrial planet, some of them are going to have hydrogen. This guy doesn't. And we can discard that at like a very, very high sigma confidence. So now, if we zoom in, I don't know if you can see this little like bluish, grayish band, but if you zoom in that spectrum, this is what you see. This is the same data. The error bars now are a lot more prominent, but still pretty much flat. And again, this is what we can tell from that flatness, because in this case, it's not as much what we see, but what we don't see. That flatness basically tells us that even if it had like a tiny little hint of hydrogen, that would be like 1,000 times solar metallicity. That's not the answer yet. This planet really does not seem to have hydrogen. We can discard that model at about 5 sigma. The planet does not have a methane-rich atmosphere. Like something like Titan does not add. So if you see that like light purple line that goes off the data points a little bit, that would be an atmosphere like Titan. This thing is not like Titan. But with the precision of this data, what we cannot tell yet is whether the planet is like Venus, like Mars, like Earth, or if it has no atmosphere. So right now, on Friday, we're putting a cycle 2 proposal to actually look at the secondary of this to actually tell if it has an atmosphere or not. And actually, with the third data point that will come in, hopefully in the summer, we will be able to make the error bars about 20% smaller, but I don't think that we're going to be able to tell, if it is a Venus or a Mars. So that was the last thing I wanted to show you. I think I'm right on time. And so to wrap up the talk, I want to go back to this slide where I was showing you the targets that are scheduled between now and the end of the year. The results that I've shown to you now, that's just the tip of the iceberg. That's about 2% of the time that we have allocated. And it's not even all the results that we have out. I can give you a heads up already. We have carbon monoxide. Like our grad students are writing that paper. We have a detection of carbon monoxide as well. And there is so much more that is coming out. Just from this 2% of the results, at least for gas giants, exoplanets is now planetary science, finally. Because just with those data, we can already answer pretty much all the questions that I posed at the beginning. We can tell how that planet formed and evolved. We can tell you what the planet is made of. How diverse the properties of these planets are. We will need all this other data to answer that one. And we will also be able to tell you how those data actually compare to other planets in the solar system. For terrestrial planets, though, we are still going to need something like the Habitable World Observatory. We will be able to tell you what terrestrial planets around M dwarfs are made of, sort of, but we are going to have a really hard time pinning it down to anything that has an atmosphere smaller than Venus, for example. So that's what I wanted to show you, and the future is bright, I would say, and I'm happy to take your questions. Thank you.
Charles. I think that's on.
So this is just a nomenclature question. You refer to metallicity, and I'm old enough to think metallicity includes everything except hydrogen and helium, but you're singling out carbon and oxygen and others.
Yeah.
So what does metallicity mean
Oh,
to
it's
you?
the same. It's still the same definition. So for people I don't know if people are hearing, but yeah, so here, metallicity is anything that is not hydrogen and helium. And so far we have seen that everything is enriched somehow. So yeah, but we are also able to now look at individual elements and elemental ratios, which is something that we could not do a year ago, and now it seems so easy. So this is going to be cool. Sure.
Yeah, the giant planets you showed that were flat spectrum, you attributed that to clouds.
Yeah.
But you didn't seem to allow that possibility for the terrestrial planet flat spectrum.
Right. Yeah.
What's the reason for?
Yeah, so if it is a fully, that's actually an excellent question. If that planet, well, first of all, it could be that it's fully cloudy, but that cloud has to be very tenuous, like it has to be like very, very close to the surface of the planet. Because anything above that, we basically would have seen a much bigger planet if that was the case. You know, if you had something like a methane-rich planet like Titan with a lot of clouds, we would have seen it bigger. And we don't. So yeah, that's a possibility. That is totally clouded out, but that level of cloud has to be tiny. That's that's a good question.
Anybody else? Oh, Charles, number 2.
Well, this is also, in some sense, nomenclature again. You didn't mention haze, and I'm never completely sure in my mind is there a distinction between haze and cloudy, and do you have anything to say?
Yeah, that's actually a very good question. So, clouds by condensation. So basically, you know, the clouds on Earth, you have water sitting around, and because of gravity, they condense. Haze, on the other hand, forms by photoionization. So you basically have to have, you know, like some kind of external irradiation in this case, and the external irradiation photodissociates whatever molecule are there, and that forms a haze. With JWST data, thankfully, we're not super sensitive to the haze because you only see it in the optical, just because the particles that form the haze are about 1 micron in size. So it shows in the optical, but what we are going to be able to do with JWST, but that will have to be with MIRI observations between 5 and 10 microns, is we are going to be able to tell you what the haze and the clouds are made of. And you know, and these are not clouds like clouds on Earth. I mean, these things are not made out of water. They're made out of magnesium silicates and stuff like that. So, but yeah, but that's the difference. Like clouds are condensation, haze is photodissociation. So.
How many of these systems that you're going to be looking at, or that you have looked at already, do you have any estimation of the age of the star?
Oh yeah. Well, to our knowledge, or that I remember, I think the large majority of them are main sequence stars. I think that there is a couple of young planets, and there is also a couple of white dwarfs, like planets on white dwarfs, which probably Andrew can tell you more about this. But everything else, I think, is main sequence. So anywhere between, yeah.
And do you have rotation periods for many of them?
Yes, and the ones that we don't, we can get them from tests, actually. Yeah. So, yep.
Especially if they're young, it's easy.
Yeah.
All right.
So when you're looking only at a small handful of transits, how much do you worry about like stochastic weather? You know, like, how would that affect these results?
Yeah, I mean, like for JWST, we don't, right? Like what we worry about, or what we used to worry about, was like things that were causing, and like basically the telescope and the instruments not being stable enough, so we would see changes between like transits of different epochs. That's not something that we are seeing. Like everything is super well behaved. We're seeing very little correlated noise, which is produced by these things. Here, everything is photon noise. We're reaching precisions, which I forgot to say this at the beginning. Remember that I said that what was reported was a goal of a precision of 30 parts per million. We're reaching precisions of 5 parts per million. So anything that is a terrestrial planet, we can do it, as you see. But to go back to your initial questions, from the ground, that has been a nightmare. And I think that that's really the limitation from the ground. It's both weather and also instrumentation that wasn't built for this. While the JWST instrumentation actually, like exoplanets were discovered when JWST, started its design. So the design includes observations of exoplanets, while everything else, including Hubble, Spitzer, and so on, this was before exoplanets even were known to exist. So none of that instrumentation was prepared for this, and that's part of the headache. Yeah. So.
Well, you set up the question I was going to ask. 60 planets in the first year,
Yeah.
and
Yeah.
lots of proposals going in on Friday.
Yes.
Is there going to be anything for the Ariel to do left over when it launches, maybe towards the end of the decade?
Well, I mean, I can tell you one thing, and this is I'm also the chair of the users committee, and there's going to be a call out for like what to do for exoplanets with JWST. And one proposal that I have is, this is a volume limited sample, right? This is not like cosmology that there is like billions of galaxies that you can look at. But exoplanets, you only have so many that you can actually observe. So one of the things I'm going to propose is to actually have a program that observes every single planet that is observable. And that is going to create a library of observations for the future that anybody can use. So hopefully, we will not have to write proposals for exoplanets in the future. But I mean, that said, that would be for two very, very specific modes of observations. Basically, near spec prism that covers from 0.5 to 5 microns, and probably MIRI from 10 to 12. But if people want to go into detail on other things, then they would have to write proposals. But that's the hope right now.
But if you want to know about the weather, you have to keep going back. So there will be something for Ariel to do.
Oh, but you're talking about the weather on the planets? Yeah. Totally. Sorry, I totally misunderstood your question. I'm not sure we're sensitive though. I haven't done calculations of like what kind of variability we would see. So I don't know. Yeah, sorry, I totally misunderstood your question. Sorry. Okay.
Okay, we're just about out of time. We're going out for the colloquium dinner at Changsha. I have 1 or 2 seats left if anybody is interested in joining us. And let's thank Mercedes again for showing us the tip of the iceberg.